So we're looking at expanding parentheses. Today it is no different. We just give it a fancy name, and we call it the binomial theorem. That's all the binomial theorem is. It's exactly what we saw before. If you expand out 1 plus x to the power of n, you get nc0 plus nc1x plus nc2x squared. In the middle there, just some general term, nckx to the k, and then the last term, ncn x to the n. We can write that using some notation to save ourselves a lot of time. And so we could simply just put the general term, which is nckx to the k, and then we're saying, oh, well, it'll be all of these, starting when k equals 0, all the way up to when k equals n. And that just saves writing the whole thing out. And nck, remember, it's the same as we saw back in combinatorics, is n factorial on k factorial, n minus k factorial. There will always be n plus 1 terms, because if you're starting at 0 and going up to n, you'll end up with n plus 1 terms. And as I said last time, just having 1 plus x can be a bit limiting. So we could extend that to be a plus b to the power of n. Our general term then becomes nck, a to the power of n minus k, b to the power of k. Although I tend to remember it the other way around. I tend to put the power on the b first, because that matches the k, and then I just say to myself, well, I know the powers have to add up to be n, and I go, oh, well, n minus k must be the other power. Okay. Evaluate 11C4 without your calculator. So that's when we go into factorial notation, and you might recall that idea of rolling out the factorials. So 11 factorial would be 11 times 10 times 9 times 8, but I'll stop there because that'll cancel with the 7 factorial, which would be the 7 times the 6 times the 5 times the 4 times the 3 times the 2 times the 1, leaving me with 4 times 3 times 2 times 1, or 4 factorial on the bottom. And then we can notice things like, 4 2s are 8, so they'll cancel. And 3 goes into 9 3 times. And now we've got a nice easy one to work out. 3 times 11 is 33, times 10, there's our answer, 330. That's how we used to do it in the good old days, when your calculators didn't have a combination button on it. You had to work it out the long way. It was fun. Right. Find the value of n. If nc5 is equal to nc8. Now, there's 2 ways you could do this. You could bring both sides back to factorial notation and then solve the equation. Or, remember those 3 Pascal triangle relationships we looked at? One of those relationships said this: nck is always equal to nc n minus k. So it's symmetric. So in other words, the 5 and the 8 must add together to give n. So if I remember that relationship, I can go, well, hey, that means n must be 13. Again, something like this. Yes, I could change everything in a factorial notation and attempt to solve that equation, but this one here also looks like one of those relationships. The ones where we were forming the numbers in Pascal's triangle, and we said to get any number, we go to the row above it. So I could say that's going to be, well, there's the relationship. n minus 1ck plus n minus 1ck minus 1 is nck, was the relationship. Now, in this case, instead of n minus 1, I've got n. I've just got to be careful with that. Which means 20, you'll notice, matches up with what I've got as n, but really, it should be n plus 1 for ours, because n is 1 more than the n minus 1. So 20 should be 1 more than the n, because the k minus 1 and k, that all matches up. So n in this case must be 19. So if I was creating something in the 20th row, I must have got it from the 19th row, add those 2 numbers together. So if you recognise those relationships, that can save a lot of work. Because otherwise, put it all back in a factorial notation and then you've got to try and solve that equation. We want to find the 5th term in this expansion. Well, I always start with the general term. And I call the general term k plus 1. Because remember, k is going from 0 to n. So when k equals 0, I just find it a bit silly saying the 0th term. So that's the only reason I go k plus 1. So I can say, oh, well, when k equals 0, I've got the first term. So, but 11ck in this case, the minus 3 on b, so it's the second term I always put to the k, and then the two powers have got to add together to give 11, so the power of 5a must be 11 minus k. So there's my general term. We want to find the fifth term, so in my notation that must be when k is equal to 4. So if I sub 4 in, I get term 5, 11c4, 5a to the power of 11 minus 4 is 7, minus 3 on b to the power of 4. Well, that answer there is obviously unsimplified. I haven't worked out the 11c4. In fact, that number, 11c4, 5 to the power of 7, 3 to the power of 4, would be quite a large number. In a lot of these questions, it's perfectly okay to leave it like that, because the numbers are quite large. If I did work it out, well then 11c4 is 330, 5 to the power of 7, 78,125, 3 to the power of 4 is 81, so we end up with that rather large number, a to the power of 7 over b to the power of 4. We're going to find the term independent of x. So it's a constant number, in other words. X to the power of 0. Which term has x to the power of 0? So I can do the same way. I'll write down my general term. Now we want to find the one which will give us x to the power of 0. Okay. I'm not going to worry about the 9ck and the 3 at this stage. All I'm interested in are the x's. So I've got x squared to the power of 9 minus k. The second parenthesis, I've changed that to x to the negative 1 because it's on the bottom of the fraction. That'll be to the power of k. We want to end up with x to the power of 0. So, using a bit of index laws, we get that the power of x is 18 minus 3k. Solving that to be 0, we get k is 6. So now I can go back to the general term and work out the number. So k is 6, so it's the 7th term. 9c6, 3 cubed, negative, oh no, negative will become positive because it's to an even power. So there it is in unsimplified form. 9c6, 3 cubed over 2 to the power of 6. Find the ratio of the coefficients of x to the power of 7 and x to the power of 5 in this particular expansion. Alright, so again, I'll start with the general term. Notice I've used the alternative notation this time for 15ck. So 15ck, the 2x will be to the power of k. I didn't bother putting in 1 to the power of because, well, 1 to the power of anything is 1. So there's no point putting it in there. K. So the ratio of the coefficient of x to the power of 7 to x to the power of 5. So x to the power of 7 will be 15c7 times 2 to the power of 7. X to the power of 5 will be 15c5, 2 to the power of 5. So I'm now going to go to factorial notation. 15 factorial on 7 factorial, 8 factorial. Dividing by, so I'll invert and multiply. 15 factorial on 5 factorial, 10 factorial. And the 2 to the power of 7 will cancel with the 2 to the power of 5, leaving me with 2 to the power of 2, which is 4. Now let's have a look at our factorials. The 15 factorial will cancel with the 15 factorial. That one's nice and easy. The 8 factorial will go into the 10 factorial. I mean, so will the 7, but I'm choosing the bigger one. So the 8 factorial will go into the 10 factorial, leaving me with 10 times 9. And then the 5 factorial can go into the 7 factorial on the bottom, leaving me with 7 times 6. So 10 times 9 times 4, 7 times 6, 60 on 7. So there's our ratio. Well, I've written it as a fraction. I suppose technically I should have written it as 60 to 7 if they've asked for a ratio. But I think it'd be a mean person that marked that wrong if you just left it as a fraction. So we shall add this to our list of questions.